Hello everyone, and welcome to my two-part lecture series here in the Geometric Analysis Festival. First of all, I would like to thank Hoju for doing such a great job at organizing this digital event and also for letting me present some of my work here. As you might recall from the introduction video, I'm presenting parts of my PhD thesis, which I'm currently completing at RWTH Aachen University under the supervision of Heiko von der Mosel. If you're interested in the lecture slides, you can just follow this QR code with your smart device or just send me an email the old school way. Alright, so let's start with the talk. And the title of my talk maybe warrants a little bit of an introduction. In particular, you see that I'm looking at high regularity of surfaces minimizing a Finsler area. I wrote a Finsler area because there are many more notions of what constitutes an area in Finsler geometry. So there will be two parts of this lecture, and in the first part I will introduce the setting, and in the second part I will talk about regularity of surfaces. So let's go to the first part. Well, first I'm going to explain to you a little bit of the setting. Maybe you don't know the Plateau problem. You might recall from the introduction video I had these wireframes and the soap films. So I'm going to show you the mathematical formulation of this. And then the second part of the first talk, I'll talk about existence of minimizers, and in particular how we can use what I call Hildebrand and von der Mosel framework for Cartan functionals. All right. Well, first, a little bit of notation. I will be looking at immersed surfaces, U, which is a map from a manifold M of typically dimension 2 into an ambient manifold N of higher dimension. And there will be different notions here, so we will look at Finsler metrics and Riemannian metrics, which have a bar on top of their letters, which will always live on the domain, and the corresponding letters without the bar will live on the target, and also points on M and N will be labeled alphabetically. And always keep in mind, in the final results we'll always have M equals 2, the disk will be the domain, the two-dimensional disk, and the target will be Rn. But most of the intermediate results, they do apply for arbitrary dimension and codimension. Okay, so let's start. What is a Finsler manifold? So here in this picture you can see a convex set, and so what picture you should have in mind is the following. This should be in R3, so pick any point Q in R3 and then look at the tangent space of R3 at that point. That's another copy of R3. And in that copy of R3, you can choose a norm, and the picture you're seeing here is the level set of that norm. So it's the unit ball of that norm, okay? And now, as you vary the point Q, a Finsler metric is a smooth family of smooth norms. So as you vary the point, this unit ball should wobble in a smooth way, okay? And it should always be the level set of a positively homogeneous convex function. So in more mathematical terms, we will see this picture again, but in more mathematical terms, I guess you can look at the following definition. Just very briefly, we won't use this in this talk here, but basically Finsler metric is a function of the tangent bundle of a certain regularity, which is positive one homogeneous, and which is elliptic. So basically this means it's a convex set. It's a convex function. And people in Finsler geometry usually also look at norms which are not symmetric, and for the symmetric ones they have dubbed this term reversible. For this talk here, this is not so important, so this is all what I'm going to tell you about Finsler manifolds. Alright, so we would like to talk about volumes, and let's assume first you have a target manifold N, so this ambient manifold, and you have an auxiliary Riemannian metric on that manifold. And well, then what you would do in Riemannian geometry, you would define the volume of this as, you can look at it in different ways. You can either look at it the Riemannian volume form that is associated to the metric G, and then define the volume as the integral of this top dimensional volume form. This only works if your target is orientable. If it's not orientable, you can still look at the volume density and then integrate this volume density. If you come from more measure theoretic side, you can also think, okay, this target manifold is a metric space with the geodesic distance as its metric, and then there I can look at the Hausdorff measure, and this gives me a notion of volume. Sometimes I also call this the Riemannian volume. Now I'm looking at this notion from Finsler geometry, and so one notion to generalize the volume is the so-called Bussmann-Hausdorff volume of the target. And basically it is what I've written down here. So you will take two structures now. You have a Finsler metric on the target, and you also have an auxiliary Riemannian metric on the target. So two competing geometric structures, and you will integrate the Riemannian volume density against a weight function. Again, if you like to think more measure theoretically, you can also think the Busemann-Hausdorff volume is a measure on the manifold which is absolutely continuous with respect to the Lebesgue measure or the Riemannian measure of the original Riemannian manifold, and the Radon-Nikodym derivative is this weight function W here. And I've written it down in this way here in the middle. What do I mean by this weight function? Well, it is a ratio, and the value of this function at point Q is the following. You take in the numerator, you take the Euclidean unit ball in that tangent space, and then you take its Riemannian Lebesgue measure of this Riemannian unit ball. Okay? And because this is the Riemannian the Lebesgue measure of the Riemannian unit ball with respect to the Riemannian metric, this will be always a constant, just a constant that you know from classical analysis. And in the denominator, you look at the Finsler ball, and then you take the Riemannian Lebesgue measure of this Finsler volume. So think of what the picture says here. You take this dodecahedron, and then you take its Lebesgue measure of this dodecahedron, and that's your denominator. So two things is what you can see here. First, if your Finsler metric is actually coming from a Riemannian metric, so if it's the square root of a scalar product, then you can choose this auxiliary Riemannian metric as that exact scalar product, and then your Finsler ball will be the same unit ball as above, and your the ratio will cancel. So what I'm trying to convey here is that in the case that your Finsler manifold is actually Riemannian, the Busemann-Hausdorff volume of this is the same as the Riemannian volume, so it really is a generalization. The second thing that you can notice here, but we'll see it on the next slide in a little computation, it's a bit strange that you have to pick an auxiliary Riemannian metric, but indeed is actually not strange, because the whole computation of this volume will be independent of the metric G. And so I've said this before, the numerator is a constant, and if I'm changing this metric G here, notice that above in the integral also the volume form here will change, and so it's upstairs and downstairs, and there will be a factor which you'll see on the next slide which will cancel. Now this was the Busemann-Hausdorff volume of the target, and we want to talk about areas. So we are looking at immersed surfaces, U, which immerse M into N, and then we are defining the Busemann-Hausdorff area functional as the volume now of the domain with respect to the pullback Finsler metric, right? So you pulling back the Finsler metric, that will be a Finsler metric on the domain. For now, I think here you need C2, so U should be C2, but later we will look at W12 functions because we will get rid of this pullback. Okay, and as I said before, this whole construction is actually independent of the choice of this metric G. So let's look at that maybe in more detail here. Here's a sketch. It's a little linear algebra fact, I guess, which I didn't know before I saw it. But given two Riemannian metrics, G and H, you can always find an isomorphism which intertwines the two. So you can always write the metric G as, well, sort of like this here. And why does this work? Just very briefly, let's consider the tangent bundle, and with this Riemannian metric G, you get an associated Ries isomorphism between the tangent bundle and its dual. So let me denote that with the same letter. And then with the other Riemannian metric, you also get a Ries isomorphism. So you're going back down here to the tangent bundle. And let me denote this here a little bit colloquially with H inverse. And then basically this bundle isomorphism E will be the composition of the two. So you can just complete this diagram, and that's what the definition of the isomorphism E is. Okay, so if you've done that, and then you will look at the corresponding Lebesgue measures and the volume densities. And what you can then do when you do the calculation is you see that there will be a factor in front, and the factor will be the same for each objects, and therefore in the functional that we looked at, one factor will be in the numerator and one in the denominator, and so they will cancel. So these are not constants, they are functions, but nevertheless they will cancel. And that's why this is independent of the choice of G. Okay, so now let's look back at this formula for the volume, for the area. Now let me remind you, we had chosen two objects, F and G, on the target, so two structures, and now we're going to pull them both back to the domain. So these are now the F bar and G bar, they are now structures on the domain M. And then the area of this surface U is this ratio which we've seen before against the volume density, and all of this with respect to the pulled back objects. And now what we're going to do is we're going to look at that in integrand in local coordinates. And what we can see is the following. We have here again in the first line what you see above. And now by definition of the pulled back objects, we can now consider the surface U as either a Riemannian isometry or a Finslerian isometry, just by definition, because we've pulled back each object, so they will push forward to where we started out with, right? So just by definition of G bar and F bar, you can consider it as either. In any case, let's look first at this Lebesgue measure in the domain with respect to the pullback metric. If I calculate this and push it forward, this will push forward to the m-dimensional Hausdorff measure of G in the target in the tangent space at point U of P. Okay, and likewise, the Finsler ball with respect to the pullback metric, well, that will be just the full dimensional ball intersected with the plane that is the tangent space of the immersed surface. Okay, So just keep this in mind for now. There's a ball here intersected with a plane. Okay, let's look at this last part here, the volume density in local coordinates. Usually what you do is, you find this in any textbook, you write this as the Gramian determinant of the metric. And this you can also write as, you take the, if you write it out, you take the partial derivatives with respect to the coordinate directions and you wedge them together. So this is an element now in the mth exterior power on the target, and so let's say at point u of p, and in this space you can, the Riemannian structure on the target induces a scalar product on this exterior power as well, and with respect to this exterior power scalar product, you take the norm of this. This will be the same as this Gramian determinant. Now notice here, this is an element of the mth exterior power, but actually it's a special element. So it will be a simple m vector, or totally decomposable m vector. And these vectors are all those vectors which are of exactly this form. So they are the m wedge of exactly m vectors. So not all elements in the exterior power can be written in such a way. They're all linear combinations of such elements, but they cannot all be written exactly in this way. So this is a subset of the set of all m vectors. It's actually a submanifold. And in particular, what I want to stress here is that this space here is not linear. So it has no linear structure. It's a submanifold of the linear mth exterior power, and this will be, keep this in mind for later or in the second talk. Okay, so let's continue. You might recall this from the introduction video where I had the wireframes and I dipped it in soap water. So this is the Plateau problem that I described there, and here's the mathematical formulation of this. So how it goes is as follows. You have some Jordan curve in space, this was the wire, and then you're looking at surfaces which are spanned by this wire, which are minimizing the area functional from before. In the class of competitors, these are all functions of the form, they're W12 functions defined on the disk, so disk type surfaces, and they parameterize the boundary weakly monotonically. So what does that mean? That means if, as you go along the boundary here in the domain, you should go forward on this boundary. You're allowed to stand still for a while, but you always have to go forward. Okay, so in more mathematical terms, the Sobolev trace of this function u should have gradient 0 at some points, but always otherwise is positive. Okay. Right. So when you think of what I did in my introduction video, I guess as a mathematician you would ask yourself, well, is this always possible, or did Sven have some special soap water available to him such that every time he dipped something in there was always such a minimal surface popping out? So the first question you would ask yourself is there existence of minimizers of this new functional? And so that's what I'm going to talk about here. And this is a theorem which we obtained a few years ago, and let me go through it with you. So here you have also a disk type surface, just as before, immersed into Rn. Well, not immersed necessarily, but into Rn. And you have these two structures, F and G. And we now need, as a further assumption, that the norms coming from these two structures, so the scalar product norm and the Finsler norm, they should be globally comparable, so they should be globally equivalent with respect to two fixed global constants on the whole tangent bundle. And also we need some symmetrization assumption, which is not so important here. So let's skip that. But then we have that for every rectifiable Jordan curve, we can find a minimizer of this functional, which is conformally parametrized. So conformal parametrization means that if you have a rectangular grid on your domain and you take the map, then it will also be a rectangular grid on the surface. And the regularity that you obtain here from this theorem is that it's continuous up to the boundary, it's Hölder in the interior, and locally it's a bit better integrable. And the Hölder exponent depends on these two constants up top. Okay, so maybe a word here, why do we need rectifiability? Well, we want to use the direct method of the calculus of variations, and for that, the class that you're infimizing over should be non-empty, right? And so if you assume that the Jordan curve is rectifiable, then this is always guaranteed. So that's why we need this here. Okay, so how did we obtain this? Let me introduce to you this framework that I've talked about before, this Hildebrand von der Mussel framework. So this is came up in works that they did in the late 90s, early 2000s, and here's the definition of a Cartan functional. So Cartan functional from the disk into Rn is a functional which has an integrand which depends on the position in space in Rn and on a bivector. So this is the partial derivative in the one direction, cross product with wedge product with the partial derivative in the other direction. So this is an element of this space, the second exterior power, which is in itself is isometric to r to the power n choose 2, right? So the dimension is n choose 2. And so this is what a Cartan density is, and it should have 3 properties, and there should all be properties in this bivector argument, in this second argument. So the first property it should have is that it should be positively one homogeneous, and it should be convex, and also of linear growth. And so linear growth here means that you take the integrand and you can compare it from above and below with the norm in this space of the argument, right? And let me remind you that this vector here, in the classical case, in codimension 1, this vector, this wedge vector, will be the normal of the surface. So if you have a surface here, then you take the partial derivatives of the parametrization, take the cross product, that will be the normal of the surface. And then we've seen this before as well, in local coordinates, the volume density will look like the norm of this normal vector. So this here, what I want to convey is that this here is the classical Riemannian or the classical Euclidean area integrand, really from classical analysis in the 50s or even earlier. Okay, so 3 properties, keep that in mind, and I'm going to talk about each of these properties and what they imply. So why do we need, or why are we interested in positive one homogeneity? Well, that is because it implies invariance of the functional with respect to orientation preserving diffeomorphisms. So if you change the parameters in an orientation preserving way, then the value of the functional doesn't change. And you need positive one homogeneity here for the orientation preserving property. If you had absolute one homogeneity, you wouldn't need to care for the orientation. And I guess that would be interesting if your manifolds that you're looking at are not orientable. And also this is something that I calculated recently, which I think was done by Mori in the 50s for codimension 1, but you can also do this in arbitrary dimension and codimension, which is the following. If you have a function and a functional which looks like this, just as in the classical calculus of variation. So you have some integrand which depends on u and the differential du, or in classical analysis you would have the Jacobi matrix of u. So it depends on u and its derivative, and if this is diffeomorphism invariant with respect to orientation preserving diffeomorphisms, then you automatically get such Cartan densities. And what I want to convey here, so this is a bit more abstract. You can write it in an abstract way and then do some formalism, and you get this Cartan density for free. And so what I want to convey here, maybe these wedge vectors, these bivectors here, they look a bit strange. If you haven't seen this before, why should we be interested in looking at such functionals? The point here is that they're quite natural for those functionals which are invariant under parameter diffeomorphisms because of this these two directions, right? Okay. So the next 2 points are the convexity and the linear growth of the integrand. And as I said this before, we want to use the direct method of the calculus of variations, and for that you need lower semi-continuity of the functional with respect to some topology. And the classical result you often use is from Acerbi and Fusco in 82, I believe, which characterizes weak lower semi-continuity in W12 as some growth condition and quasi-convexity of the integrand. And indeed here, if the integrand of this bivector is convex in this bivector variable, we can look at, again, this variation, this version of the integrand written as the Jacobi matrix. Then this new integrand is polyconvex, so that's a buzzword you can look up, which implies quasi-convexity, which is what we need for Acerbi-Fusco for the functional. Okay, and 2 more remarks. So very important 2 remarks. The 3 above conditions, so as you see them, they're guaranteed, that they do guarantee the existence of minimizers. So if we can meet these conditions, then we don't need to prove anything, because it already is a theorem in this framework established by Hildebrand and von der Moser. Right, and I said this before, they did this in works spanning the early 2000s, and we are going to see this in the second part of the lecture series, where we look at higher interior regularity, where we need a bit more conditions on the integrand, and also, which we're not going to do today, the regularity at the boundary, where you usually need regularity of the boundary curve. Should be more regular. Okay? Good. So let's define a Catal functional for our area functional. A Cartan integrand, Cartan density. So this is what I'm going to do here. I'm going to define a density here, which will be defined on the set of simple vectors in this tangent in the exterior power of this tangent bundle. And the definition is what we've seen before. You have a point in space, and you have the corresponding m vector, and then you write it as this ratio times the norm of this vector. So this is the standard Euclidean area integrand, and here's this weight function we've seen before. There's the Hausdorff measure of the ball intersected with this set here. And what do I mean by the set? Well, that's the set which this is an m-dimensional subspace of the tangent space at Q, which is spanned by this simple m vector. So if you don't know this, here's another buzzword that you can look up. So this is called the Plücker embedding, which gives you the ability to identify m-dimensional planes with m vectors, or simple m vectors more precisely. So there's a mapping between the Grassmannian and the projectivization of the simple m vectors. And you need simplicity of the m vectors here, because otherwise this subspace will not be m-dimensional, would have lower or higher dimensions. Right. So now we've done that, and because we did the calculation earlier, now we can also write our functional as the integral over such a function here. And if we choose m equals to 2, then we're exactly in this form, right? We have a point in space and we have a bivector for m equals 2. So this is our definition of the Plateau integrand, which is restricted to m equals 2. Now, we wanted to show these properties. So here, let me show you some results which were already available. The first one you can already see from the definition. Actually, this integrand here is one homogeneous, because you have here only the norm, and if you scale the vector by some factor, then the norm will be absolutely continuous. And here you have this m-dimensional plane which doesn't change, which is invariant under scaling of the m vector. So it's absolutely one homogeneous. We have a bit more than we need. And also, I said this before, this is only defined on the simple vectors, but actually we want it defined on the whole space, because we need convexity, and convexity is a linear condition, so it should be a vector space or a vector bundle. And there are two results here, which the first one is an old result by Busemann. In codimension 1, this is guaranteed by him. And for domain dimension 2 and in arbitrary codimension, there's this paper by Burago and Ivanov from 2012, which guarantees a convex extension of this integrand. And here is the theorem again. I told you before in the remarks that we need three conditions for existence. One was the positive homogeneity, the second one was the convexity, and the third one was the linear growth. And the linear growth condition, you can use this comparability of the norms to translate this into a comparability of the area integrands, right? And then you get the linear growth condition, and then you automatically, from this Hildebrand Fornamosel framework, get this regularity result, this existence and lower regularity result. Okay, so here are a few references if you are interested. So there are these papers, and I think this second one here is a survey paper, and these last two are quite long, but they're very well written, and you can read all of the analysis that they did there to come up with these results. Actually, this one maybe is the reference for the second lecture that I'm going to present to you. So it's a lot of analysis, but yeah, you can look it up here. And also let me mention another group which who are working on a related problem in metric spaces. So they look at a whole class of area functionals in metric spaces. And this is the group by Alexander Lütschak and his student Paul Kreutz, and also Stefan Wenger and his student Martin Fitzi. So they're both in Cologne and Fribourg in Switzerland. And they look at this metric space setting, and they get also very interesting results there, where they, due to the nature of the metric space, they can't go higher in regularity than we will see in the second part of the lecture. But they do look at a more general framework, so this is also very interesting. And let me show you a few images to pique your interest to keep watching the second lecture. So here I will show you numerical calculations that we did with my colleague Henrik Schumacher here in Aachen. And on the left you will always see the Enneper wire, the boundary curve here. This is the Enneper wire. And you will see a numerical minimizer of the area functional. And on the right, you will always see the unit ball of the corresponding Finsler norm that we choose. So here in this case, we on this slide here, you can see the Euclidean norm. And also let me say, this will always be a constant Finsler norm. So at each point in R3, you will take the same norm. So it will not be a family, but will be a constant Finsler metric. And in this case here, this is really just the standard Euclidean metric, and on the left you will have the numerical approximation of the N-per surface. Now let's look at what happens if we change the metric. So here we go, and on the left we can see that something appeared here and here. And if we look at the dodecahedron, which we saw at the beginning, then we can see that even more flat surfaces appear here, and something interesting is starting to happen. And we can also look at a more extreme example where we really get a flat or almost flat surface here, and then kind of smooth ridges, or at least they appear by a visual check to be smooth, right? And if you tilt this pyramid on the right, if you tilt this a little bit, also these smooth ridges, they will also tilt. So this is kind of interesting, and yeah, I don't really know what's going on here mathematically, but well, maybe this piqued your interest and you're going to keep watching in the second part of the lecture. Very happy to see you back in the next video. Bye!